Okay, so last video covered the kind of thing you should have already known from before. But now what I want to do is introduce you to a way that you can visually represent a complex number. And you can do it on what is known as an Argand diagram, which is just basically a sort of an x-y axis. But instead of having an x-axis, what you have is a real. And then where your y-axis is, you're going to have an imaginary, okay? And you can just draw in lines to show where these are. So you remember all numbers are actually complex numbers, because all numbers, all the real numbers are just numbers that with imaginary part 0. So 3 is a complex number, and it has 3 as its real part. So let's just say 3 is there. And it doesn't have any imaginary parts. It's just a straight line over here. Okay. Now, what about Z2, complex number 4 plus 3i? Well, that would suggest that we've got 4 in the real plus 3 in the imaginary. So maybe somewhere like this. Okay. So again, this would be the complex number 4 plus 3i. You're basically plotting it on this diagram. This diagram is called an Argand diagram. Okay, we can do Z3, which is just purely imaginary. So that would be, say, something like this. It's 5i. It's 3. Minus 3 minus I might be something like this. Okay, minus 3 minus I. Z6 is remember this, is the conjugate pair for Z2. So Z2 conjugate would be equal to 4 minus 3i. So it would be somewhere like this. Spot that it would actually have a symmetry, so that angle would be the same as that angle. That will be useful later. This angle is the same as this angle. Okay, so we can plot things on an Argand diagram, and we're plotting them onto what is known as the complex plane. Okay, so we're now representing all numbers that could possibly exist, not on a line but on a plane instead. Okay, now what we can gather from this, let's just say here is an Argand diagram with a complex number on it. Okay, it's got a complex number on it, Z. Then each complex number has a modulus, and what I mean by modulus, it has a length. It has a length, and this is the modulus of Z. It's that distance from here to here. So just like with a vector, the magnitude of the vector. The modulus is like the magnitude of the complex number, the size of it. What it also has, it has an angle, and the angle is always measured from the real line in a anti-clockwise direction. So start from here and I measure round in a clockwise direction. So even if I get one, let's say like this, here is my complex number, then the angle, then the angle is measured like this. Okay, always from the positive real around in an anti-clockwise direction. You can do it in this direction if you want. Obviously, it will be just slightly different. Again, that will be useful in a minute. So just bear that in mind. So we could have measured it this way and we'd have got the same answer. But we tend not to. We tend to do it like this. Okay, hope that makes sense. Now, the angle that is made from the positive real in an anti-clockwise direction is called the argument. The argument of the complex number. Okay, so complex numbers have a modulus, which is the same as the magnitude, the size of that number. An argument is the angle made from the positive real axis in a clockwise direction. Okay, and that is really, really, really useful. So let's just have a little look at this. let's first of all, if you want to do this, let's make an Argand diagram. Okay, so we're doing 1 plus 3i. 1 plus 3i. So that would be, say, 1 plus 3i. Say somewhere like that. Okay, and what we know is that this distance is 1 and this distance is 3. So how are we going to find the modulus of z? Well, we can just use Pythagoras' theorem. It's 3 squared plus 1 squared square rooted, which is going to be what? The square root of 10. So that's the sort of the size of the complex number. And what is the argument? Well, the argument is this angle here, measured in a anti-clockwise direction from the positive real. So a little bit of trigonometry can help here. We can say that the tan of that angle is equal to the opposite over the adjacent. So tan theta is equal to 3. So theta equals arc tan of 3. And I'll just use a calculator to work out what that is. Shift tan to the minus 1 of 3. And make sure you're working in radians. Most of the time we work in radians. That is 1.25 radians to 3 significant figures. Okay? So there is the argument of that angle as well. Now, just be really, really careful. Let's do part B. Part B says we've got a slightly different one. So again, let's make an Argand diagram. Argand diagrams really, really help. We've got minus 1 plus 3 this time. So that would be somewhere like this. And this distance, because it's, we're talking about distances, so this is 1. It's not minus 1. It's 3. So actually it's going to have the same modulus. The same modulus, which is going to be the square root of 3 squared plus 1 squared, which is going to be the square root of 10. Now, we need to know what the argument is. Well, the argument is this angle here. So clearly, it's basically going to be 180 minus this angle here. Okay? Or pi minus that if we're talking about radians, which is what we should be doing. So the argument is going to be, well, tan theta is equal to 3 over 1. So theta, this is theta, is equal to 1.25. So the argument of z is actually going to be pi minus that angle. So use a calculator, shift pi minus the answer gives me 1.89 radians to 3 significant figures. Okay, I hope that makes sense, because you've got to make sure you measure the right angle. This is not the correct angle. That wouldn't be the argument. Okay, again, hope that makes sense. I'll stop the video there. Let me know if anything is